In this video, we're going to do an AP Physics 1 FRQ, where we have a card of mass M initial moving with negligible friction along the track as shown in figure 1. In scenario 1, the card is released from rest at point A at the top, which is at a height H initial above point B, which is at the bottom of the hill. At point B, the section of the track forms a circular arc with a radius r. And then as the cart passes through point B, the apparent weight of the cart is weight initial. So first we're asked the height of the hill is doubled in our scenario 2, which we see is 2h initial instead. And we want to indicate whether the apparent weight of the cart as it passes through the same point B in scenario 2 is greater than, less than, or equal to our weight initial by writing one of the following. So when we see that we pass through B, we go down, and then we go through the circular loop, and then we go down again back to B. So what can we think? Well, when we're at point B, we're still at the bottom of this curved track, so the center of the circular arc is going to be above. So that means that you are going to need a net upward force in order to curve upward. So in scenario 2, we start from a greater height. So it's going to reach point B with a greater speed than if we were in scenario 1. So a greater speed means that the object is going to need a larger inward centripetal force because of that larger V. So since FG is still going to be the same and is still going to be down, we still have FG acting down. Our track has to push up with a larger normal force in order to support. So that is why we are going to need a greater weight. Now, for part B, we're asked to justify the response using a qualitative reasoning beyond referencing equations. So our reasoning is that because we have our centripetal force acting upward still, and we still have the force of gravity acting downward, we are going to need a larger V for that larger centripetal force, mv squared over r. So that's why we're going to need a larger normal force, because we still have force of gravity acting downward and we need to counteract that. So then for part B, we're asking, use in conservation of energy or Newton's second law, derive an equation for our weight of the car as it passes through point B in scenario 1 in terms of height, radius, mass, and physical constants as appropriate. Begin your derivation with fundamental equations. Okay, so what we do here is, when you're at point A, we see that we have our UG equal to potential energy, M initial, GH initial. Kinetic energy is going to equal to 0 because we are going to start from rest up here. And also apparent weight is just the same thing as normal force. So we can use conservation of energy from point A to point B as our comparison points. So now when we are looking at point B, we have our potential energy equal to 0 because we start at a height that is 0 here, and kinetic energy is 1/2 m initial VB squared. So when we write our conservation of energy equation, we have A on the left side and B on the right side. So that's kinetic energy plus potential energy is equal to kinetic energy plus potential energy. So kinetic energy cancels out here, and then potential energy cancels out at B. So then we just write our equation right down here, and then this equation right here. We can see M cancels out, so our mass does not depend. So we are going to have 2gh initial is equal to 1/2 VB squared times 2, because we want to cancel out that 2. So that's why we multiply both sides by 2 there. Then we take the square root of both sides to get this expression for VB. But we actually want to keep this expression here so that we can use it later. The reasoning is because over here at point B, we can see that the normal force is always acting perpendicular to the point of contact of the floor. So that means that's your normal force pointing towards the center of the circle. You're still going to have your force of gravity acting downwards, which is equal to your weight, M initial times G. So then after that, you can just look at the summation of your forces in the radial direction. That's going to equal to M initial VB squared, which makes sense. That's just your M, your F is equal to MA, times your acceleration. Your centripetal acceleration is always equal to V squared over R. So then that's how we plug that in. Now, our normal force is acting in the upward direction, so it's going to be a positive value. And then acting in the downward force is our weight. So then we have normal force minus M initial G. So then if we solve for normal force, we just add our M initial G to both sides, and then we get this expression here. So we see that we have a VB squared here. And earlier we found that over here. So then you substitute this in right here, and then you get this form. We can move the 2 to the front to make it look more simplified. And then we get this equation. We know that our weight initial is equal to the normal force, so this is just our expression. And then here, all we did was factor out that M initial G to get this simplified form. Now, for part C, we are asked to justify how the equation derived in part B is consistent or not consistent with your reasoning in part A. So when you have our scenario 1, we have our weight initial is equal to m initial g plus 2 m initial g h initial over r. So then scenario 2, the only thing that changed was that your height was doubled, so you had 2h initial as compared to h initial here. So then you have your exact same equation basically. So weight 1, weight 2 is going to be m initial g plus 2m initial g times 2h initial, all divided by r, and it's going to be the same thing, m initial g plus, here we can multiply that 2, 4m initial g h initial, all divided by r. So then we can compare what is different between these two equations. Well, we can see that it's just going to be this component right here. We know that 4m initial g h initial is going to be greater than our 2m initial g h initial over r, so our weight 2 is greater than our weight initial. So doubling the height is going to increase the speed at v, and that increases required centripetal force, so the normal force apparent weight is going to be greater.